Assalamualaikum and a very good afternoon. Okay, welcome to my class KNC 2113 Thermodynamics 2. Okay, right. So this will be your second lecture, which is on the theory of solutions thermodynamics. Okay, the objectives of the study this lecture will be on how to develop a more comprehensive fundamentals property relationships and extends it to scope to often phases of variable compositions. And it's also to introduce you the definitions of chemical potentials and to understand partial properties for interpretations of individual species such their existing solutions. And also you're going to be exposed to the term fugacity for mixture of ideal gas in order to provide the basis for treatments of real gas mixtures, as well as the excess properties for idealizations of ideal solutions. Okay, so the fundamental of property relationship, okay, right? So the first would be the total Gibbs energy of any closed system is defined by this, okay, right? So which is, hold on, let me pull on my laser pointer. Okay, is D, and Gibbs energy is a function of the volumes and pressure, entropy, and the temperature. So if we can expand into this term here where the temperature is a constant as well as the number of mole. Right? So you got this, if you cancel this, you got the same values, and also for the temperature and the number of moles like this, in which in previous uh, studies we can define it into this, right? In the previous lecture was NV, right? G delta G and G equal to NV dP minus N entropy delta T and the summation of the chemical potential here. Okay, right? Okay, this is for number of species. Okay, right? Okay, right. For special cases where there's one mole and the number of mole R is equal to Xi. Okay, right? So we send it to this, and then the equation is changed to this. Okay, right? So from this, from equation 11.2 and for equation 11.3, where summation of total number of mole is 1, so we can rewrite the parameters into this. Okay, right? For volume is dg over p at dx, constant t and x, number of mole, right? And then delta for entropy is delta g over t p over x. Okay, right? And from here also we can expand it to enthalpy, which is G plus Ts. Okay? This gives energy, temperature, and entropy. So it can be written into this form. Okay, so when Gibbs energy is expressed as a function of canonical variables, it plays the role of generating function, providing the means for calculation of all other thermodynamic properties by simple mathematical operation, differentiations, and elementary algebra, and explicitly represent complete property information. Okay, this is this is let me back first. Okay, this is what is meant by here, okay, right? So we can replace the values and then we can create a new equations, okay, right? So if you know the basic equations and you apply it into the actual equations, so that's what I mean. Okay, for two-phase fluids, okay, right? So we can denote it as alpha and beta, okay? Either one can be vapors or another can be liquid, okay, right? But it doesn't really matter. So we just assume it to be alpha and beta to indicate that there are two phases, okay? So we apply the previous equations, right, into this form here, the alpha and beta here, okay, right? Where subscript alpha and beta identify the phases, and it assumes that the equilibriums are imply uniformity of T and P. What does it mean is that in liquid form and the vapor form are in the same pressure and temperature. So it is in equilibrium. Remember when I told you that when it is in equilibrium, mean that the 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 change, right, the evaporations and also the condensations occur at a constant rate where both are the same. So The process is still occurring, but at this constant rate that we perceive it to be, it's constant. Okay, that is defined as the equilibriums. So the quantity for D and I can be is independent and arbitrary. Okay, right? So the chemical species alpha and beta should be the same. Okay, right? Because the rate are the same. Okay, so for other numbers of species present in the systems, it should be the same. Okay, right? So that's why it's very important we define it to be in equilibriums. So if it's not in equilibrium, then the process will shift to whatever directions. Okay. Okay, you will learn that in reactions. Okay, right? So where some process will react more to increase in pressure or increase in temperature. Okay, a similar but more comprehensive derivation show that for equilibrium T and P must be the same for all phases. Okay, right. So let's define partial properties. Okay, it's a definition of chemical potential. I think you have known it before, partial properties, that it can define as this. Okay, MI, okay, M can be any other chemical thermodynamics properties. Okay, this is to be seem to be almost close to, okay, or it seem to be equal to as constant pressure, temperature, and others number of moles. Okay, so we are interested in one species, which is species I. Okay, and the molar property method, okay, M is the molar property, and the partial property denoted by over bar. Okay, this is the over bar, and the symbol therefore is M over bar here. Okay, this is partial properties. I think you have covered this in physical chemistry. And then for solutions properties, you don't have any values there. Okay, right? It's a solid alphabets. And partial property, you have a bar. Okay. Okay, you have a bar on the top here. Okay, denote by that. Okay, you can apply. Okay, you can apply this molar properties to volume, internal energy, enthalpy, entropy, and Gibbs energy. And also for pure species, okay, it denote by I. Okay, that I here. Okay, there is I, pure species properties. What does it mean? Pure species mean that it does not have any mixture. Okay, from comparison with question 11.1 and 7, we found that the chemical potential is equal to the partial molar Gibbs energy. Okay. Okay, right. So the definition of partial molar properties provide the mean calculations of partial property from solution property data M. Okay, this is M, number of mole times the molar properties, and it's a function of T, P, all the number of mole of other chemical constituents. Okay, right? And the total differential of M, we can define it into this. Okay. At the change of temperature, constant T and mole, constant pressure and mole. Okay, you can see, right, guys? You can cancel this, it will be the same, right? And also this is the number, constant pressure, temperature, and other species, right? Except I. Okay, okay, this is explained here. Because the two partial derivative on the right are evaluated at constant n, okay, this is constant n, then we can simplify it into a simpler form, okay, right? So in this case, we can take out the m here, n is constant, okay? So in the equation is almost the same, okay? Because partial molar is actually the ratio here, okay, that mole ratio of the total mole, okay, right? So we can put in, okay, exchange it into x here, okay, right? So that is x, okay, to manipulation. Okay, so this is the basic, okay, this is the basic equation for changing molar properties, okay, right? So this is a change constant I x change in m, but this constant m change in x. Okay. Other general equation for the m use the Gibbs to Herm equations here. Okay, right? So it's this thing, you can see it very similar, and it should be equal to 0. Okay, right? So this equation must be satisfied for all changes in P and T and M caused by the changes of state in homogeneous phase. Homogeneous phase means that when there's at least you have two mixture, it's all the same, right? Both for the liquid and also in the vapor form. Okay, right? So this should be equal to 0. Why? Because this constant, that's constant. So because this becomes 0. Okay, rationales for partial properties. The partial property concept implies that solution property presents a whole, the sum of its parts, or represented by partial properties M of the constituent species. Okay, by definition, we got this earlier, which yield the partial property for total properties. Okay, these are total properties. Okay, these are summations, right? Summation, and all the uh, constituent species. And this gives the Helms, okay, equations. Okay, right. So for a binary system, okay, so in this course we only consider two combination of two species. It can be more complicated, but for the beginners we just consider two. Okay, this is what two species. This is what we call as the binary systems. So M is x1 m1 plus x2 m2. Okay, right. Hence dm. Okay, right. So if we differentiate this dm to each of this component first, dm, right? That differentiate that to this component, and we differentiate this to this. This is the differentiation of this component here. But when m is known, the function of x1 at constant dmp, the appropriate form of the function is expressed as here. Okay, right? Because this should be equal, okay, right, in equation 14, 11.14, okay, right here. Right, summation of xi dm are equal to 0. Okay, right? So both of this value is the combination summation of this value will be 0. Okay, right? And we know that x1 plus x2 equal to 1, and differentiation we got this, and then eliminating the x2 in favor of the 1 in equation B here, then we got this equation. Okay, so alternatively we can change that and enter it into x2, and this is for the x1. Okay, so that's a very straightforward mathematics. Okay, this is what it means by the previous statement here. Okay, this is what I mean by these statements. Okay, right? So we can manipulate the equations by through differentiations and integrations. Okay, where am I? Hold on, guys. Okay. Okay, I think I'm done. Okay, right here. So from equations 11.8, we can say that chemical potential is equal to the Gibbs energy. Okay, right? So we can return it into this form here, and application of exactness yields the Maxwell equation relations. Okay, right? So this is been done earlier. Okay, right? In the previous lecture in your thermo 1. So this is the equation here. Okay, and then we found that Gibbs energy as constant T and X. Effect of pressure is related to the volume. Okay, this is okay the change of temperature at constant pressure and x mole, right? So it's related to entropy. Okay, right? So every equation that provide linear relations among thermodynamic properties of constant composition solutions has its counterpart and equation connecting the corresponding partial property of each species in the solution. So we can manipulate all the equations that you know and then turn it into partial properties. That's what does it mean. Okay, an example is based on the equation here. Okay, so everybody know this. Enthalpy is equal to internal energy plus PV. Okay, right? And then in terms of moles, okay, we can put N in the front. Okay, right? Right? And V here, and then we differentiate Ni at constant T and P and J yields this equation here. Okay, right? So this constant P, T, and J. Okay, this constant T and U also, right? And then this is the P. Okay, right? So the equation is become, okay, this is a partial enthalpy equal to partial internal energy plus PV, partial volume. Right? Pressure is constant. Right? So this is the volume, partial volumes. Okay, right? So in the constant composition solution, G is the function of P and T, and therefore, okay, right? So now we manipulate it again at constant T and X, okay, right here, and it yields this equation here. Okay, the GV partial G, the change in partial G equal to volume, partial volume dP minus entropy, partial entropy dt. Okay, the ideal gas mixture model. Okay, right. So this part is limited ability to describe actual mixture behavior. The ideal gas mixture modules provide a conceptual basis upon which to build the structure of solution thermodynamics. Okay, right. So it is useful properties module because it has a molecular basis, approximate reality in the well-defined limit of zero pressure, is analytically simple. Okay, so I think we have seen this before from equation this for volume, right? So if we assume it to be in ideal gas, Ig is ideal gas for species I, we can write it into this equation here. But V, we know that PV from PV equal to nRT, then we can rewrite it into nRT over P here, right? And then since these values are constant, right? T, P, and J are constant, then we can take it out here, and only this, right? Delta Ni are constant in J, okay, right? And then go to RT over P, okay? Change in N, change in Ni. This is constant. So what does it mean? Mean that this change is equal to that. So that's equal to 1. Okay, for ideal gas, given T and P, the partial molar volume, the pure species molar volume, and the mixture molar volume are identical. Okay, right? Partial ideal gas here, molar volume. Okay, right? This is for the whole, right? And then for that species, okay, this is a pure species, and then for the whole. Okay, right? Okay, we assume that others are constant, right? Okay, others are constant, J are constant. Okay, the ideal gas mixture models, okay. The partial properties, I think we have done it earlier, PR is YI over VIG, okay. Okay, what is YI? Y is the mole fraction of species I, okay, that is in the previous lecture. And the partial pressure obviously sum with the total pressure, you know. So with this, from the Gibbs theorems, then we can define that the enthalpy is equal to Yi, okay, this equation here, okay. This is for the entropy, okay, and this for the Gibbs energy, okay, right? I think we have done seen this before. An alternative expression of chemical potential, right, mu ideal gas I result for when G is replaced by expression given in T and P independent. Therefore, the ideal gas, okay, this G V I G D P. Okay, let's go back. It's from where's that? Okay. Lost. Where is it? Here. It's okay. We just move on. Okay. For an ideal gas, okay, for an ideal gas, DGIG or BIGDP, okay, this is from previous lectures, okay, and then RT over P, you got this value here, the change of P, right? So if we need to integrate this, we need to find IG, then we need to integrate this and this, okay? So since T is a constant, then we got this function here. It's an integration constant at constant T, okay, right? And then this RT ln P, okay, right? And then the chemical potential, is equal to the Gibbs energy. We assume to be equal, and we from this equation here. This is the for integrations of the constant. Okay, and G, Ig, and this. Okay. Okay. Now we will introduce you to the term fugacity. Fugacity is a property that takes the place of mu Ig, but which does not exhibit its less desirable characteristic. Okay, right? So you can see this equation here from previous, right? Here, okay? It's a function of P, okay? But and then this for species I, we denote it as Fi. So the new property with the same unit of pressure replaces P in equation 11.2, the previous equation. So we know that for fugacity of pure species for ideal gas condition is equal to P. So we can rewrite it here for real gas minus the ideal gas should be equal to RT ln fugacity of uh, for this Fi here divided by P. Okay, right? Okay, this is Fi is for the fugacity for the partial species I. Okay, so I think you have done this before, that we have the residuals, right? Remember, the residual is how far the result is varies varies from the actual. Okay, nah? If the residual is equal to 0, indicates that the gas behaves like an ideal gas. Okay, right? So Gi minus Gi, this is the RGI. Okay, right? So it's equal to RT ln phi here. Okay, phi, how we define phi? Phi is basically a ratio of fugacity species I to the total pressure. Okay, right? So these are new properties, and we call this as fugacity coefficients. Right? We get a symbol 5 here. Okay. Okay, that this equation is applied to pure species I in any phase at any condition. However, as a special case, they must be valid for ideal gas. Okay, so for ideal gas, as I mentioned to you that is similar to the actual gas. Okay, the actual gas will be and actual gas will be the same. So G arm should be 0. So when this is 0, then phi should be 1, isn't it? Because 1 here, then the power of 0, right? Okay, so 0 put the front, then 0. Okay. Okay, so the application of loan by equation P permit evaluations by integral of, okay, don't this equation 6.49. Okay, I think we have seen this before. Okay. And then for Z, Z is the compressibility factors. Okay, right? It depends on the second viral equations. Okay, B double I here, I get P, and then we got this. Okay, so this is, you guys can see that how we can relate certain properties, and we know the other equation that we can combine together to form a new equation here. Okay, the evaluation of fugacity coefficients to cubic equations. Can remember we have the van der Waals, Redlich-Kwong, Sol, Rachleigh and Kwong, and Peng Robinsons. Okay, right? So we can use this equation here, and this all this value you can find it in from the in your appendix, right? The tables. Okay. Okay. Equation 11.3, which define fugicities of pure species I, may be written for species I as saturated vapor and saturated liquid at the same temperature. Okay, so let's say we have vapor liquid equilibrium. Correct? So we have vapor here, gives energy for vapor. Okay, we apply this. Okay, this indicate vapor, and this is indicate L indicate liquid. By difference, we can get this and minus that. So this value cancel each other because it is in equilibriums. Right? Okay, and the equation apply here, we found that the fugacity for vapor at species I is equal to the viscosity of liquid of species I, which is equal to also the viscosity of the saturated. Okay, okay, this is applied for vapor liquid in equilibriums. Like I say here, for a vapor species coexisting, liquid and vapor phases are in equilibrium when they have the same temperature, pressure, and viscosity. An alternative formulation is based on the corresponding viscosity coefficients. Okay, right? So this is saturated, this is the ratio, or okay, this is the viscosity coefficients. Same thing. Okay. Okay, the viscosity of your species as compressed liquid may be calculated from the product of easily evaluated ratio. Okay, so we have this, you can see here, this P cancel, this cancel, this cancel, and cancel. So left that, okay. So this ratio here is the vapor phase viscosity coefficient of your vapor I at its vapor liquid saturation pressure designated by Phi I saturated, okay, which we can use this equation here. Okay, right? And then for the liquid, right? For the liquid, it's a very weak function of pressure. Remember, I told you when in a liquid phase, pressure, there hardly much pressure will not affect the volume or the properties of the liquid. So at temperature well below TC, at critical temperature, okay, mixture, right? Mixture. Remember the yields, right? The temperature below the yields there. Okay, it will not affect the pressure, will not have much effect. So an excellent approximation is obtained when this volume, the liquid volume, which is I, is still constant at the value of saturated liquid. For this case, okay, so we can assume it to be this, okay, right? Because we don't need to integrate, just this P, this is the temperature difference here, okay? So we don't need just a temperature difference because there's not much change in pressure, effect of pressure to the liquid. So this is called as a pointing factors, and this can be get from the table. Normally the value is given. Okay. And ZV is given in question 20, the simplest form of the viral equation. Then V, okay, is the second viral equation here. And then we can find what is a viscosity of species I, okay, for the vapors. Right? Okay, viscosity and viscosity coefficients species in solutions. Okay, right. So in the solutions, okay, right. So the definition of viscosity of a species in solution is parallel to the definition of pure species viscosity. For the viscosity ice in a mixture of real gas or in a solution of liquid, the equation analogous to equation 11.29, the ideal gas expression is this. Okay, right? Okay, remember? Okay, right? But this is very similar what you can see earlier, 11.29, but we have a cap here. Okay, okay, this cap is the viscosity species in solution, replacing the partial pressure YIP. Okay, right? Okay, this definition of viscosity in solution Fi does not make it partial molar property and is therefore identified by a circumflex rather than by the overbar. Okay, overbar is the partial, overbar is the straight line, right? So you have a circumflex there, means it is in the solutions. Okay, so we can define it here. Okay, for the solution Fi alpha, this should be the same. Okay, it's the same like in the partial properties. Okay, so for the partial molar property, we have the residuals, isn't it? This is the partial residuals equal to the actual minus the ideal gas here. This also apply for Gibbs energy. Okay, and then subtracting 11.29 from 46, both for T and P. Okay, right? So you can do your maths later. And we find that mu I minus mu ig equal to this, okay? Okay, this equation here. And then the result from the one here, combined with that, we found that the residual Gibbs energy is this. Okay, right? Okay, right? And this is the phi with a cap. Okay, right? In a solution, we call it viscosity coefficient of species I in solution. Okay, although it's most commonly applied to gases, the viscosity coefficient may also be used for liquid. Okay, but for liquid, we have a cap here for solutions. Okay, for an ideal gas, it's a special case. Okay, right? Then viscosity Ig is equal for this. Okay, okay. Thus, the viscosity of species I in ideal gas mixture is equal to its partial pressure. However, okay, this viscosity coefficient of species I in solution is equal to 0 for another gas, then residual will be 0, right? Okay, in other gas, okay, so this should be the same, okay, 1. Now, y1 IP in the viscosity coefficient in solution also it's the same as this, so this become 1. So the 1 then is 0. Okay, the fundamental relationship between these is put into an alternative form through mathematical identification. Okay, right. So this is a mathematical identification. I think you guys can go and look at the mathematics, okay, right? In which you derive this. Okay, this equation here will relate Gibbs energy, volume, yeah, enthalpy, and Gibbs energy here to the uh, mole. Okay, and then this is for it's the different here. Okay, right? This okay. This for the whole thing. Okay, right? Some that whole thing, and this for the ideal gas. Okay, right? And this for the residual. Okay, guys, look at this. This no, the whole thing to the whole system is the ideal gas. Oh, I'm sorry. This is the actual. This is the ideal gas, and this is the residual. Okay. Okay, the fundamentals. Okay, the fundamental residue property relationships. Okay, right. So we got this equation previously. Okay, right. From this we can manipulate that with various equation here. Then we got this VR, a constant T and X at the change of pressure. This is for the constant P and X, change of temperature, and this is when P temperature and other species constant but change in I. Okay, so you guys can see that is all we're repeating what we have done earlier. Okay, so it's still the same process. Okay, now viscosity coefficient from viral equation of state. Okay, so we have seen this before. Z values, right? From 1 plus Bp over RT. This is B is from the second viral equations, which can be written into this form here, and we can expand it, right, into this. Okay, that B can be in this form here, but we know that right. Bij equal to Bji. Okay, right? So binary equation I, 1 and 2, and J and 2 expansion is given by this. Okay, right? So this is y1 square, this is this, and these are the same. We got 2, and then that's y1 square. Now, this mathematics. So the two final equations have appear B1 and B2 for which subscript are the same, and B12 for which two subscript are different. Okay, right? I already explained that. So we go just here. For equation 11.62, right? So we can allow derivation or expression for ln these and these, right? So obey it become this. Okay, so z partial z, okay, can be written into this form here, and substitution of this parcel Z into 11.60, then we got these equations. And where the integration is elementary because P is not a function of pressure. All that remains is the evaluation of its derivative. So this does not affect, the pressure does not affect this value B here. Okay. Secondary coefficients. Right. And therefore, we can get this viscosity coefficients here to this form, and then we can rewrite it into this form, and then it become a bit more complicated. Okay, okay, generalized correlations for the viscosity coefficient. So for this generalized, right? So P is equal to P critical times P reduced. Okay, right? Okay, or the change of P equal to PC times P reduced here. Okay, so hence we can put in this value into the previous equations. Okay, right? And then we got this equation here, and then we integrate it into Z. Okay, right? So we got the in this form here. Okay, this is the first. Okay, we can in this form here. This is related to that, and this related to that. Okay, we can write it in that form. Okay, so for this, you will can for the values is provided by Lee and Kessler. Okay, you can go to table E1 to E4 in appendix E. Okay, so you have this value and you just calculate that. Okay, right? So multiply that. Okay, extensions to mixture. Generalized correlations this described is for pure gases only. The remainder of this section shows how the viral equation may be generalized to allow calculation of viscosity coefficients. Viscosity coefficient that phi here, so for solution in gas mixture. Okay, right? So we have seen this equation before, right? This and then for the function equation 3.65 previous lectures, then we can get this omega, right, for stake also. Okay, right? So we can get this equation here. This is the critical INJ temperature, pressure, and the Z values. Okay, don't worry guys how they got this, because if in the exam I will give you these equations. Okay, I don't expect you to derive these equations, but it's good enough for you to know that how to apply these equations. And this for the volume also. Okay. Ideal solution model. Okay, so for chemical potential as given by the models, we can write it into this equation here. Okay, right? And then there is for ideal gas. But for ideal solution, we can put ID there. Okay, ID means ideal solutions. So you have ideal gas on the top of the two mixture, then you have ideal solutions. Okay. We define ideal solution as one for which, okay, this equation here, where the subscript ID denotes an ideal solution properties. Mole fraction is here represented by Xi to reflect the facts that application is most often to liquid. Okay, so solution is for liquid. However, a consequence of this definition is that an ideal gas mixture is a special case, namely an ideal solution of ideal gases, for which Xi in this equation here is replaced by Yi. Okay, right? So in gases, this is Y. In ideal solution, it is X. Other thermodynamic property for an ideal solution follow the 11.75. Okay, right? So we can see here it's the same. Okay, right? Except we just change Ig into Id. Okay, how you derive it also. Similarly, see here, this is for the volumes. This is for the entropy. Okay, right, guys, and also this is for the enthalpy. Okay, right? So overall, we can, the summability relationship applied to a special claim for ideal solution is this. Okay, uh, the molar properties ID equal to this. Okay, for ideal gas, this is Y, but for solution is X. So we can yield this equation here. It looks very similar, isn't it, for ideal gas? Okay. Okay, Lewis Randall's rules. Okay, Lewis Randall rule says that the viscosity of ideal solution I is actually Xi Fi viscosity here. Okay, and this equation applied to each species in the ideal solution at all condition, temperature, pressure, and compositions. It shows that the viscosity of each species in ideal solution is proportional to its mole fractions. Okay, this mole fraction here. The proportionality constant is the viscosity of pure species I. Okay, this is pure species I in the same physical state as the solutions and at the same temperature and pressure. Okay, right? So division of both sides. Okay, this equation, and then in the previous one, okay, right, we can cut this. Okay, right? So this is the an ideal solution. Okay, right? I and this. Okay. Okay, so excess properties. Previously, you have learned residual properties, isn't it? Residual properties is where you compare the real gas to the ideal gas. So the smaller the difference, the more the real gas behave like an ideal gas. Okay, it's also the same for the for solutions, which we define it as excess property, in which the molar property, excess molar property is equal to the actual minus the ideal solutions. And this is, you can apply for Gibbs, enthalpy, entropies, right? And then you apply over here, Gibbs energy equal to H minus Ts here. Okay, right? So if we deduct, okay, right, Me for a mixture, okay, right? So we have for a mixture, we have um, vapors and also liquid. Okay, right? For liquid or for the solution, we have Me here. And for the vapor, we have Mr. So we can get this equation here. That is minus MID minus MIG. Okay. Okay, so this is the excess properties. Okay, right? So we can manipulate it around using all the various equations we have done earlier. So we can get it into this form here. Okay, the difference of molecular property of ideal solution minus molecular property of ideal gas is equal to this summation here, right, of residuals. Where the summation term have been cancelled, this lead immediately to, okay, this. Okay, all right, okay. Because this, for this, we replace that. Okay, that's how we got this. Okay, and then this is for the partial relationship, is the same thing. Okay, and we can also apply it for the excess for Gibbs. Okay, the previous equation 11.55. I'm sorry, 11.55 earlier. Yeah, right? So it's the same. So these are comparisons between the molar properties, right, to G, to residuals, and to the excess. If you can see all the equations are the same, except they are changed into R or E. Okay, the excess keep energy is of particular interest. The equation will be written as, okay, right, so we do it again here. Okay, right? In this form here, viscosity, and then this the ideal solution, and then we find the deduct here. Okay, when we deduct here, what is this, guys? This is a GE, isn't it? Right? And then we got the RT viscosity solution to the X, right? And then this value here can be written as gamma, right? So this, I think it's gamma here. Yeah, this is gamma. And this gamma is what we call as activity coefficients. So it's very similar to fugosity coefficients. Fine. All right. So hence GE is equal to RT ln gamma here. Right? And then we can manipulate it around, okay, right? And then we got this, okay? So we can rewrite it into this form here, right? So chemical potential for other gas is this here. Other gas, so it's Y, okay, vapor form. For other solution, it's X, okay, right? And for the whole thing, for the system, right, solution, this is the activity coefficient time, the solutions, right? Fraction. Okay. And then we can manipulate it around. Can I? It's the same thing, guys. Can I? Previously it's for residuals, but now it's for excess. Okay, right? Okay, so all of this. Okay, the nature of excess property relationships. Okay, and the partial and these. Okay, hold on. Okay. Equation 11.96 demonstrates that loan activity coefficient is a partial property with respect to GE over RT. It is analog to this equation and the same relation to this and this. Okay. So if you look at the equation here, it's very similar. This is applied for the vapor and this apply for the solutions. So you can see that the equation are very much is the same. Okay. Okay, and we also can apply it to GE, HE, and SE as in this term here. Okay, right? And access property are strong function of temperature, but at normal temperature are not strongly influenced by pressure. Okay, why is that? Because it is in liquid form, isn't it? We already defined that in liquid form. Pressure does not affect much of the properties, but the temperature does. Okay, but somehow if the temperature is very high, okay, higher than the critical temperature, then pressure does affect the solution. Okay, the nature of excess properties. Okay, although the system exhibit a diversity of behavior, they have common features. Okay, all excess property become zero as other species approaches priority. And although GE versus X, here is approximately parabolic in shape, both HE and TSE exhibit individualistic composition dependency. When an excess property ME has a single sign, as does GE in all 6 cases, the extreme value of ME, maximum or minimum, often occur near the equimolar compositions. Okay, what does all these three means? Okay, so if we plotted, okay, right, into a graph here. Okay, when it's 0 means that it's pure species 2, right? So 1 is pure species 1. Okay, so when it's pure species, everything is going to be 0. There's no excess. So it behaves like a pure properties. Okay, so this is what they mean by this. All excess property becomes 0 as other species approaches purity. Okay, so purity all is 0. Okay, now all is 0 here. 0, 0, 0, 0. Okay, the second one it says, although GE is parabolic, but of both HE and TSE exhibit individual composition dependency. Okay, GE is always parabolic. You can see here parabolic, GE parabolic, GE parabolic, here parabolic, parabolics, and parabolics. Correct? But TS here is parabolic, but not here. See, it have their own behavior. Okay, and the third one says that when it's all parabolic or all in the same sign, the maximums of the deviation occur at equimolar. Okay, at the center here. Okay, that's how we deviate more than excuse me, deviate more at the equimolar. Okay, so for further reading, please read your sorry, overview reading, please read your books, right? It's more detailed in there. If you have any questions, please do not hesitate to ask me. Okay, thank you very much, and and see you around.